A powerful earthquake deep beneath southern Italy has once again drawn attention to one of the most geologically active regions in Europe. The event was not centered beneath a famous volcano, nor did it rupture dramatically along the surface. Yet its effects were spread across a remarkably wide area, raising questions about the hidden forces operating far beneath the Italian peninsula. Why can a deep earthquake be felt hundreds of miles away while a shallower one sometimes affects only a limited area? Why does seismic activity in southern Italy immediately draw attention toward Campi Flegrei, Mount Vesuvius, and Mount Etna? And why are authorities and residents alike paying such close attention to every significant tremor occurring beneath the complex meeting point of the African and Eurasian tectonic plates? At approximately 10:12 in the evening, Coordinated Universal Time on June 1, 2026, a magnitude 6.2 earthquake struck beneath the Tyrrhenian region west-southwest of Sicily in southern Italy. According to seismic data, the earthquake occurred at a depth of approximately 151 miles, or 243 kilometers, beneath the surface. Although the epicenter was located offshore, the unusual depth of the event allowed seismic waves to travel efficiently through the Earth's crust and upper mantle, enabling shaking to be felt across a vast portion of southern Italy. The earthquake occurred near latitude 39.325 degrees north and longitude 15.780 degrees east, placing it offshore west of Calabria. This region lies within one of the most complicated tectonic environments anywhere in the Mediterranean. Unlike areas dominated by a single major fault, southern Italy exists within a network of interacting geological structures that have evolved over millions of years through the collision and convergence of continental plates. The Mediterranean basin may appear relatively calm on a map, but beneath the surface it represents an active boundary zone where the African plate continues moving generally northward against the Eurasian plate. The process is neither simple nor uniform. Sections of oceanic crust are being forced downward into the mantle, mountain ranges continue to evolve, and deep structures hidden beneath the sea are constantly reshaping the geological framework of the region. The earthquake's depth immediately distinguished it from many of the destructive earthquakes commonly associated with Italy. Most damaging earthquakes occur at relatively shallow depths, often within the upper 12 to 19 miles or 20 to 30 kilometers of the crust. Shallow earthquakes tend to generate stronger ground motions near the epicenter because the seismic energy has less distance to travel before reaching the surface. In contrast, the June 1st earthquake originated far deeper within the Earth. At approximately 151 miles, or 243 kilometers, beneath the surface, the seismic waves had a long journey upward. As a result, surface shaking near the epicenter was reduced, compared with what might be expected from a shallow magnitude 6.2 earthquake. However, the same depth allowed seismic energy to spread over an enormous area. Residents far from Calabria reported feeling the earthquake because the waves traveled efficiently through deep geological structures before emerging across southern Italy. The broad distribution of felt reports illustrated a characteristic feature of deep focus earthquakes. Instead of producing severe localized destruction, these events often generate moderate shaking across regions hundreds of miles apart. People may experience swaying, vibrations, rattling windows, or movement of hanging objects even at considerable distances from the epicenter. Maps of reported shaking indicate that the earthquake was felt throughout much of southern Italy. Areas of Calabria, Basilicata, Campania, Puglia, and Sicily experienced varying levels of shaking. The extent of the felt region prompted immediate public interest regarding several of Italy's most famous volcanic systems, particularly Campi Flegrei near Naples, Mount Vesuvius overlooking the Bay of Naples, and Mount Etna in eastern Sicily. The mention of these volcanoes is not surprising. Campi Flegrei has been attracting significant attention because of ongoing ground uplift, increased seismicity, and continuing geological unrest. Vesuvius remains one of the world's most closely monitored volcanoes due to its history of explosive eruptions and proximity to densely populated communities. Etna, meanwhile, continues to rank among the most active volcanoes on Earth, producing frequent eruptions and ongoing volcanic activity. Whenever a substantial earthquake occurs in southern Italy, questions naturally arise regarding possible links between regional seismic events and volcanic systems. The reality is more complex than simple cause and effect. The June 1st earthquake occurred at a depth and location associated primarily with tectonic processes rather than direct volcanic activity. Deep earthquakes in this region are generally connected to the subduction of ancient oceanic crust beneath southern Italy. As portions of the descending slab sink deeper into the mantle, stresses accumulate and are periodically released through earthquakes occurring far below the surface. Campi Flegrei, Vesuvius, and Etna each possess their own geological systems, magma reservoirs, structural characteristics, and sources of unrest. Although all exist within the broader tectonic framework of southern Italy, a deep earthquake beneath the Tyrrhenian region does not automatically indicate an imminent volcanic change at any of these volcanoes. Nevertheless, the earthquake served as a reminder of how interconnected Italy's geological environment truly is. The same tectonic forces responsible for creating mountain ranges, generating earthquakes, and shaping the Mediterranean basin also contribute to the conditions that support volcanic activity. Among the three volcanic systems, Campi Flegrei arguably attracts the greatest concern from a seismic perspective. Unlike the classic cone-shaped profile of Vesuvius or Etna, Campi Flegrei is a vast caldera system extending beneath heavily populated portions of the Naples metropolitan area. The caldera formed following enormous eruptions tens of thousands of years ago and continues to exhibit signs of unrest today. One reason Campi Flegrei receives such attention is the phenomenon known as bradyseism. This process involves gradual uplift and subsidence of the ground surface driven by changes within the volcanic system below. During periods of uplift, the crust is subjected to increasing stress. As that stress accumulates, earthquakes occur. Many of the earthquakes recorded within Campi Flegrei during recent years have been relatively small. However, even moderate earthquakes can pose challenges because of the dense urban environment surrounding the caldera. Buildings, roads, utilities, and historical structures are all vulnerable to repeated seismic shaking. A magnitude 5 earthquake occurring directly beneath Campi Flegrei would represent a very different situation from a deep magnitude 6.2 earthquake beneath the Tyrrhenian Sea. Magnitude alone does not determine danger. Location and depth are equally important. A shallow magnitude 5 earthquake beneath Campi Flegrei could generate intense local shaking across the Naples region. The combination of shallow depth, urban density, aging infrastructure, and existing geological unrest means such an event could potentially cause structural damage and widespread disruption. This explains why seismic activity within Campi Flegrei receives such close scrutiny. By contrast, the June 1st earthquake occurred more than 150 miles, or 240 kilometers, beneath the surface. Although larger in magnitude, much of its energy dissipated before reaching populated areas. Consequently, the earthquake was felt across a wide region, but did not produce the concentrated destructive effects that a shallower earthquake might have caused. Mount Vesuvius occupies a unique place in the public imagination because of its historic eruption in the year 79. Rising above the Bay of Naples, the volcano remains active even though it has not produced a major eruption in recent decades. Continuous monitoring tracks seismic activity, ground deformation, gas emissions, and other indicators of volcanic behavior. The June 1st earthquake generated renewed discussion regarding Vesuvius because residents throughout Campania reported feeling shaking. However, feeling an earthquake does not necessarily indicate that a volcano has been affected in a significant way. Seismic waves regularly pass through volcanic regions worldwide without triggering eruptions. Etna presents another fascinating case. Located on Sicily's eastern coast, the volcano experiences frequent eruptions and persistent geological activity. Its position reflects the complicated tectonic interactions occurring beneath the central Mediterranean. Magma rises through fractures and conduits influenced by regional tectonic structures, making Etna one of the most dynamic volcanoes on Earth. Reports suggesting that the earthquake was felt in areas associated with Etna highlight the extraordinary reach of deep seismic waves. The distance between the earthquake source and eastern Sicily demonstrates how efficiently energy can travel through the geological framework of southern Italy. The earthquake also underscored the significance of deep-focus seismicity in the Mediterranean region. Although less common than shallow earthquakes, deep events provide valuable information regarding processes occurring far below the Earth's surface. Scientists studying such earthquakes gain insights into the behavior of descending tectonic slabs, the physical properties of rocks under extreme pressure, and the mechanics of plate interactions at depths rarely accessible through direct observation. Every significant deep earthquake effectively becomes a natural experiment, revealing information about structures hidden beneath hundreds of miles of rock. Southern Italy's geological history has been shaped by these forces for millions of years. The Apennine Mountains, Calabria, Sicily, and the surrounding seas all bear evidence of tectonic deformation associated with plate convergence. Ancient ocean basins have opened and closed, mountain belts have risen, volcanic systems have developed and evolved. Earthquakes continue to mark the ongoing adjustment of the region. Historical records demonstrate that Italy has experienced numerous damaging earthquakes over the centuries. Some originated along faults within the crust, others occurred within deeper tectonic structures. Each event contributed to a growing understanding of the hazards facing communities throughout the country. The distinction between deep and shallow earthquakes remains particularly important. Two earthquakes with identical magnitudes can produce dramatically different outcomes depending on their depth. A shallow event may generate severe local destruction. A deep event may be felt over a much larger area while causing relatively limited damage. For residents of southern Italy, the June 1st earthquake provided a tangible example of this principle. The shaking was widespread enough to attract attention across multiple regions, yet the great depth reduced the likelihood of severe surface impacts. Transportation systems, communication networks, and emergency management agencies all benefit from understanding these differences. Rapid assessments following an earthquake rely heavily on information regarding magnitude, depth, location, and regional geology. These factors collectively determine the probable intensity of shaking and the areas most likely to be affected. The event also highlighted advances in modern seismic monitoring. Networks of instruments positioned throughout Italy and the Mediterranean can detect earthquakes within seconds, estimate their characteristics, and distribute information rapidly. Such capabilities are essential in a region where tectonic activity is a constant reality. Italy maintains one of the world's most sophisticated geological monitoring systems due to its combination of seismic and volcanic hazards. Continuous surveillance extends across fault zones, volcanoes, and regions experiencing ground deformation. Data collected from these networks help authorities evaluate evolving conditions and communicate risks to the public. Even when earthquakes do not cause significant damage, they serve an important function by reminding communities of the dynamic environment beneath their feet. Geological processes operate continuously regardless of whether they are immediately visible at the surface. The Mediterranean region occupies a unique position within global tectonics. Unlike the broad oceanic spreading centers of the Atlantic or the massive subduction zones of the Pacific, the Mediterranean contains a dense mosaic of interacting microplates, fault systems, and volcanic provinces. The resulting complexity generates a wide range of seismic behaviors. The June 1st earthquake emerged from this complexity. Its depth suggests association with structures descending into the mantle beneath southern Italy, where remnants of ancient oceanic crust continue their slow journey downward. Temperatures, pressures, and stresses at such depths differ dramatically from conditions near the surface. Understanding how earthquakes occur at these depths remains an active area of research. Rocks subjected to enormous pressure behave differently than those in the shallow crust. Processes involving mineral transformations, dehydration reactions, and stress accumulation may all contribute to the generation of deep-focus earthquakes. Regardless of the precise mechanism, the event demonstrated that significant seismic activity continues within the deeper portions of the Mediterranean tectonic system. These earthquakes may be less destructive than comparable shallow events, but they provide critical evidence regarding the ongoing evolution of the region. Attention inevitably returns to Campi Flegrei whenever major seismic events occur in southern Italy. The caldera's recent history of uplift and earthquake swarms has heightened public awareness. Residents understand that seismicity forms part of the broader picture of volcanic unrest. The key distinction is that Campi Flegrei's most concerning earthquakes are generally shallow and directly connected to processes occurring beneath the caldera itself. A magnitude 5 event in that environment would represent a serious local hazard because the energy would be released close to populated areas. This reality explains why authorities closely monitor every change in seismic patterns around Campi Flegrei. Earthquake frequency, earthquake magnitude, ground deformation, and gas emissions collectively provide clues regarding the state of the volcanic system. The June 1st earthquake, although substantial, originated far from the caldera's shallow unrest zone. Its significance lies more in illustrating the scale and complexity of Italy's tectonic environment than in signaling an immediate change within Campi Flegrei. For Vesuvius and Etna, the same principle applies. Both volcanoes exist within an active tectonic setting, yet each possesses its own internal dynamics. Regional earthquakes can be felt across these volcanic areas without necessarily producing meaningful changes in volcanic behavior. As seismic waves from the magnitude 6.2 event propagated through southern Italy, they effectively connected multiple regions through a shared experience of shaking. Calabria, Campania, Basilicata, Puglia, and Sicily all became part of a single seismic event, despite being separated by considerable distances. That widespread reach may ultimately become the defining characteristic of the earthquake. Rather than causing concentrated destruction, it demonstrated the remarkable ability of deep earthquakes to transmit energy across large areas. Residents who felt shaking far from the epicenter experienced firsthand the influence of geological processes occurring more than 150 miles, or 240 kilometers, beneath the earth. The earthquake also reinforced a broader reality about life in southern Italy. Beneath the coastal cities, mountain ranges, volcanic landscapes, and historic communities lies a tectonic system that remains active and evolving. Earthquakes, volcanic activity, and crustal deformation are not isolated phenomena, but interconnected expressions of forces that have shaped the region for millions of years. The magnitude 6.2 earthquake west-southwest of Sicily did not produce the catastrophic consequences often associated with major seismic events. Its depth prevented the most severe outcomes. Yet the event succeeded in drawing attention to the extraordinary geological setting of southern Italy, where deep tectonic structures, active volcanoes, and densely populated communities coexist within one of the most dynamic regions on Earth. From the Tyrrhenian Sea to the slopes of Etna, from Calabria to the volcanic fields of Campi Flegrei, the earthquake served as a reminder that the Mediterranean remains a landscape in motion. The forces responsible for shaping Italy's past continue operating today, often hidden far beneath the surface, occasionally revealing themselves through powerful earthquakes that can be felt across an entire region and beyond. The broad area over which the earthquake was reportedly felt also highlights an important aspect of seismic risk that is often overlooked by the public. Many people associate earthquake danger exclusively with the magnitude number itself, but seismologists have long recognized that depth can dramatically alter the effects experienced at the surface. In this case, a magnitude 6.2 earthquake occurring at a depth of approximately 151 miles, or 243 kilometers, released a large amount of energy, yet much of that energy was dispersed across a vast region rather than concentrated directly above the source. The result was an event capable of being noticed across much of southern Italy while avoiding the extreme localized damage that a shallower earthquake of similar size might have produced. The location of the earthquake is equally significant. The Tyrrhenian region west of Calabria has experienced deep earthquakes for decades, reflecting the continuing descent of tectonic material beneath southern Italy. This process is not occurring over years or centuries, but over millions of years. The slab of crust sinking beneath the region continues to deform as it moves deeper into the mantle, generating stresses that occasionally exceed the strength of the rock. When that threshold is crossed, an earthquake occurs. Events such as the June 1st earthquake provide rare glimpses into geological processes unfolding far below the depth reached by even the deepest drilling projects. For communities surrounding Naples, the event inevitably renewed attention on Campi Flegrei. Although the deep offshore earthquake and the caldera's ongoing unrest arise from different geological mechanisms, the comparison illustrates why local seismicity at Campi Flegrei is monitored so carefully. A magnitude 5 earthquake occurring directly beneath the caldera would release far less total energy than a magnitude 6.2 event, yet its shallow depth and proximity to urban areas could make it considerably more disruptive. Buildings experience shaking based not only on earthquake size, but also on distance from the source and the characteristics of the underlying ground. In densely populated areas, those factors become critically important. The earthquake also serves as a reminder that southern Italy occupies a unique position where multiple geological hazards overlap. Few regions in Europe combine active volcanoes, significant earthquake potential, ongoing crustal deformation, and complex plate interactions within such a relatively small area. Campi Flegrei, Vesuvius, Etna, and the deep seismic zones beneath the Tyrrhenian Sea are all products of the same broader tectonic environment, even though each behaves according to its own internal processes. As monitoring networks continue analyzing data from the event, the magnitude 6.2 earthquake will likely become another valuable reference point in understanding the hidden architecture beneath southern Italy. The tremor may have originated more than 151 miles beneath the surface, but its effects were felt across a region whose geological future remains closely tied to the powerful forces still reshaping the Mediterranean today.